Our last, and certainly not least, presenter is Dr. Martin Elvis. He's a highly cited astrophysicist with over 30,000 peer citations, has used most large space-based observatories to publish some 450 papers on supermassive black holes, seen as quasars out to the edge of the universe. Lately, concerned about the growing cost of space telescopes, he's turned to researching the astronomy needed to enable asteroid mining with a view to cutting those costs radically. He's published widely on issues related to asteroid mining and the space economy. He is unduly proud that he is probably the first professional astronomer to visit the Harvard Business School on business. He obtained his PhD in X-ray astronomy in 1978 in the UK, has worked at the Center for Astrophysics at Harvard and Smithsonian ever since on a series of space X-ray telescopes, culminating with the Chandra X-ray Observatory. He's a fellow of the American Association for the Advancement of Science, a member of the Aspen Center for Physics, and is past chair of the Hubble Space Telescope Users Committee and of the High Energy Division of the American Astronomical Society. Asteroid 9283, Martin Elvis, is named after him, and we're very honored to have him here today.
Thank you. I'm going to talk about prospecting these great resources we have in space because, whoop, another thing, there we go. They are vast resources, totally dwarfing the plausible available materials we have on Earth, but they are elusive. They are not easy to find. You would think they are, but not. I'm going to talk about asteroids first and then the moon, because the moon is the more near-term example. So asteroids. We've heard a lot about it. Asteroids come from collisions between planetesimals, and planetesimals are objects from the beginning of the solar system that differentiated through radioactive heating into, like the Earth, into a core, crust, and a mantle, and then got broken up. So the asteroids we see are typically more or less pure core, pure crust, or mantle. The core is metallic, the crust is silicate rock, and the mantle is full of carbonaceous materials because it never got heated up much. Okay, so there's the two pieces of interest are the metallic iron core and the carbonaceous crust, because the core is rich in precious metals, or can be rich in precious metals, not all are. Those precious metals are worth about $50 million a ton on the Earth, and that's great, so why don't we go after them? Because it's the richest of them still only has about 30 grams per ton of these precious metals. So it's a big energy-intensive extraction process at the asteroid, which is a demanding technology for now. Instead, the carbonaceous crust can be up to 10% water. It can be bone dry, depends on the asteroid. And in space, that has historically been worth about $50 million a ton. And as we just heard, the cost, of course, is coming down as launch costs come down. So this is an interesting question. The problem, of course, with that is right now there is no one to buy it in space, and so we've heard a lot about developing markets for that, so I won't go on any more about it. But the key point I want to stress about asteroids and in the moon too is that not every mountain is a gold mine, as you're well aware, and neither is every asteroid rich in any of these resources. About 85% of asteroids, of meteorites, and thus of asteroids, are stony and not very interesting. They eventually may become sources of material, valuable material, but that's not the first place you look. It's really the 5% metallic and 10% carbonaceous asteroids that are the interesting ones. And of those, in each case, only about a quarter of them are rich in either precious metals or water, right? So we're looking at 1 or 3%, depending on what you're looking for, of all asteroids are worth going after. And the ones we know about, Joel, I think, emphasized we must go for low delta V objects, like ultra low delta V objects. Right now, only about 3% of even the near Earth asteroids are accessible to current rockets, meaning you can get a decent sized payload there, at least a ton. That's what was sent to Bennu, for instance, on OSIRIS-REx. And that means that the numbers right now that are actually accessible and worth more than $1 billion is something like a couple of dozen. And that's of the ones we now know about, right? That isn't the total that's out there. My estimate is that that will grow because of surveys and because of better rockets, notably Starship, that by about 2030, we'll have about 400 of them. And by then also, we will know which ones they are, at least a good guess at which ones they are, as I'll get to in a moment. So first, we have to find the key rocks. So there's going to be 2 important surveys coming up. NASA is going to launch the Near Earth Object Surveyor in about 2025 for a 5-year survey mission looking for near Earth asteroids. Its motivation is to find the dangerous ones that could destroy civilization, which would be, not a good day. But there's a side use in that survey data will also find all the carbonaceous asteroids, which tend to be very dark, darker than fresh asphalt. And so very hard to see in reflected sunlight. But they're going to look in the infrared, 5 to 10 micron radiation, if you want to know, where they glow brightly from their black body radiation. This will give us the most likely water-rich objects. The orbits will be accurate from this. And they'll get sizes to, I think, around 10%. I need to check that out. And they will find all the asteroids, near-Earth asteroids, down to about 50 meters in diameter. And so that's very good for water resources. Of course, there are many smaller ones, and Joel emphasized this, but they will only see those if they come very close. The other big survey, which was delayed by COVID, it should have started this year, but will probably start in 22 or maybe 23. Chile, where the telescope is situated, was hit very hard by COVID. And telescopes and work on new telescopes shut down for a long time. It will perform a legacy survey of space and time, which will cover the entire sky every night. And the system is designed to find asteroids, among other things. It will be a 10-year mission, not 28, it'll be 32, excuse me, being run by it's being funded by NSF, National Science Foundation, at the National Optical Infrared Laboratory. And this is different. It's going to find, it's looking at reflected sunlight, so it finds the high shiny asteroids, the high reflectivity ones. It will use 5 different bands of the optical spectrum to image the sky, so you can get the colors of things. And that's very good for picking out the stony asteroids, the large fraction of stony asteroids. Because if you look at the spectra of asteroids, this goes from in the blue on the left to the infrared on the right for all these different types of asteroid. The stony ones are at the top, and you see they all have this characteristic flattening at the longward end, the red light end, where the red light is suppressed relative to the blue light, and that's characteristic. And it's absorption due to silicate rock, and it allows us to throw them away. Asteroid scientists will be very upset by that. You don't throw away such lovely data, but from a commercial point of view, it simplifies our search by factors of about 5, which is great. You put the 2 together, by the way, they won't quite see exactly the same objects, but that will give you a good measure of albedo, which again will tell you if they're particularly dark. That will show them up very well. And after that, that'll be great. That'll be a great time to be doing in situ prospecting. We won't, from the size and the type of asteroid, you get an idea of how much mass is in that object. You don't have an idea because 80% of an asteroid is typically void because it's a rubble pile, it's just empty space. So you really need to measure the mass by going in and with a small spacecraft and seeing how it accelerates towards the object, the asteroid. And you also need to measure in detail the actual water content or the the platinum group metal content. There may also be ways of doing that from a smallish telescope in Earth orbit. 1 to 2 meter infrared spectroscopy mission would be an interesting thing to look at, either privately or publicly. Now, the moon. The key thing about the moon is it's not just it's not just, all the resources are concentrated into quite small areas, just a few kilometers across. So it's not magnificent desolation, as Buzz Aldrin called it moments after stepping onto the moon on Apollo 11. We've made this little table of the possible resources available with my collaborators, Alana Krodakowski and Tony Milligan, based very much on the review by Ian Crawford, by the way, which is well worth reading. Most of these resources would be for in-space use. And the big example, which we've heard a little about already, are the permanently dark regions or craters that we heard about from Josh Mankin. They go down to temperatures just a few tens of degrees above absolute zero, few tens Kelvin. That makes them unique places for doing science. For instance, infrared telescopes could be hundreds of times more sensitive there. The regions are small, maybe 20 to 40 kilometers across, just a few kilometers if you really want the coldest possible ones. Now we've heard that these regions retain volatiles from the early bombardment of the first 500 million years or so of the solar system's history, when asteroids and comets hit the Earth and the moon like together. And that leads to lots of resources. We've heard mostly about water, but other volatiles will be there. There'll be organic molecules in unknown amounts. The purest water might be in a very restricted temperature range because this plot shows the temperature and the sublimation temperature for various materials. Water is, if it gets above 110 degrees in a vacuum, it will sublimate out. So it's colder, it's got to be colder than that. And its hottest temperature anywhere through the 18.6 year lunar cycle. You very quickly get other organic molecules associated with that too. And when mercury is nasty stuff, both for personal use and bad for machinery. So you need to get rid of that. And that has a higher sublimation temperature. So it's going to be quite tricky to find the best places for this. And that will need a lot of prospecting, which is tricky in permanent darkness. The resources in general on the moon are concentrated, it's not just the water resources at the poles, but here, for instance, is a thorium concentration map from Lunar Reconnaissance Orbiter. Initially, they orbited at 100-kilometer altitude, and you've got this map of thorium abundance from the gamma ray detector there. They then orbited 3 times lower and now have about 30-kilometer resolution. And you see the clumping up of the distribution of thorium. Let's compare these two maps again, right? As you get better resolution, things get more clumped and richer. The concentrations get higher. So we could be wrong about the concentration of these materials. And in particular, if you look at the 1 pixel in that region, which is the central red circle there, that contains a lot of topography. So there's plenty of room for much more localized and higher concentrations. We don't know about these yet on almost any scale because all the surveys of the moon so far have been global. They've scanned the entire surface of the moon to do a first order resource assessment. It seems to me that this is now the time to prospect these hotspots, the potential resource hotspots in much more detail. And if you're going to mine, you really need to get down to scales below about 100 meters, something like that, to make it plausible. We could do that first from orbit by having telescopes and instruments in general designed to not to scan the whole surface of the moon, but to point at these hotspots. And you can probably get down to the 100-meter like scale. And once you get down to there, then you've made it plausible that you can raster scan with wheeled vehicles over that 100-meter square scale area, whereas doing it over kilometer scales is getting pretty tough. So if you can do it from orbit, you do it from orbit. And that's a missing link, I think, in our plans so far for prospecting. So who are the prospectors? So right now, I've talked about government agencies for those 2 surveys, the NEO Surveyor and the Rubin Observatory Legacy Survey of Space and Time. The great advantage of that for all parties is that the data is public and it's public worldwide. It's not necessarily true that non-US agencies will make the data 100% public. That's just not known necessarily. Although there's plenty also of room for private companies to pick up on some of these areas, like the lunar orbiting hotspot measurements, or certainly the plans of Deep Space Industries and Planetary Resources to send prospecting vehicles to asteroids. This is good. Private companies, unfortunately, go defunct, which is sad, but it's just a feature of capitalism. So the big thing is that if a private company does this, then very much they are not going to tell you about it. It will be their intellectual property. It will be a way of raising funding from different rounds. And that means it may be duplicated, but that's okay. So space resources in conclusion, space resources are abundant, but they are concentrated and mostly unmapped at a scale that is useful. And how they should be prospected for depends on what we think we want to achieve in space. Should it always be public? Should it be private? Should we have public-private partnerships? And we've heard a little bit in favor of that already. And I'll just leave you with those thoughts. Thank you. And there is a book you can read a lot more about prospecting asteroids, at least, that just came out, and I recommend it. I found it quite interesting. Thank you.
Thank you, Martin.